Hello everyone, welcome back to Chemical Engineering and Aspen channel. In our today's video, we will focus on the topic of heat exchanger, but in today's lecture, we will again focus on the same part which we started previously, which was number one to do the manual calculations, number two to do the Aspen simulations, then to compare both the manual results and the Aspen results to check the reliability of the model. Previously, we have taken the distillation column module, and now today we will be taking the heat exchanger module. The video will be divided into three parts. Number one is the manual calculations using the information from the problem statement. Number two, using the information from the problem statement, do the Aspen simulation, and finally we will compare both manual and Aspen simulation results. So before starting the video, if you have not subscribed to the channel yet, please subscribe to the channel. Click on the bell icon to get all updates related to this channel. So the problem statement is that a shell and tube heat exchanger is used to cool hot water with cold water. Hot water enters through the tube side of the heat exchanger with a mass flow rate of 0.03 kg per second and at a temperature of 80 degrees centigrade, and it needs to be cooled to 30 degrees centigrade. Cold water enters the shell side with a mass flow rate of 0.06 kg per second with an initial temperature of 20 degrees centigrade. We will assume atmospheric pressure throughout the system. Since we know Q is equal to mCp dt or Q1 is equal to Q2, either mass flow rate or temperature is unknown. We are given the mass flow rate, we are given the temperature at the three sides, inlet and outlet of the hot side and inlet of the cold side. So obviously we now need to know the outlet temperature of the cold water. So this is our problem statement for today's activity. So the first part is the manual calculation, which we will be going through now, that we know the standard equation Q is equal to mCp dt. For this case, the total heat transfer may be obtained from the energy balance considering the adiabatic heat exchanger. So we say Q1 is equal to Q2 or Q of H is equal to Q of C. Now Q of C is M of C, mass flow rate of the cold fluid, Cp of the cold fluid, temperature of the cold fluid is equal to mass flow rate of the hot fluid, Cp of hot fluid, temperature of hot side. This is the delta T of C, this is the delta T of H. Now we know mass flow rate of hot side is 0.03 kg per second. The delta T of hot side is 50 degrees centigrade as the inlet temperature is 80 degrees centigrade, outlet temperature is 30 degrees centigrade. That comes out to be 50 degrees centigrade. For Cp, we will take the average of the inlet and outlet. So we need to know the Cp at the inlet, which is at 80 degrees centigrade, and then at outlet, which is 30 degrees centigrade. So Cp for water at T is equal to 80 degree is 4.198 kilojoule per kg degree centigrade, while at 30 degrees centigrade, the Cp is 4.179 kilojoule per kg degree centigrade. Taking the average of these two values will give an answer of 4.1885 kilojoule per kg degree centigrade. So accordingly, we get the heat transfer rate from hot stream or hot side to cold side or hot stream to cold stream is 0.03 kg per second, which is mass flow rate, 4.188 kilojoule per kg degree centigrade, which is Cp, and then multiplied by delta T, which is 80 minus 30. So accordingly, the answer is 6.28 kilojoule per second. Now we need to calculate the outlet temperature or the outlet water temperature. So Q is equal to mCp delta T. At this point, we do not know the value of delta T. Also, we do not know the value of Q of C. But the amount of heat transfer from the hot side or hot stream to cold stream is equal to the amount of heat gained by cold stream. So Q of C is equal to Q of H. So now we know the value of Q. M is 0.06 kg per second. We will take Cp at the inlet point because we do not know the outlet temperature. So the Cp at the inlet point is 4.183 kilojoule per kg degree centigrade. Delta T of C is equal to Q of H divided by M of C into Cp of C. So Q of H is 6.28, that is equal to Q of C. Mass flow rate is 0.06 kg per second. Well, the Cp of the cold side at 20 degrees centigrade, obviously we can now take the value at one temperature, so that is 4.183. So delta T of C comes out to be 25 degrees centigrade. Now that delta T of C is equal to T out minus T in, or T out is equal to T in plus delta C. Obviously, T in is 20 degrees centigrade, delta T is 25, so accordingly, the cold water outlet temperature from the heat exchanger after exchanging heat with the hot stream is 45 degrees centigrade. We have applied material balance, we have solved it, and we found out the temperature to be 45 degrees centigrade. Now we go to the Aspen calculations and we will see whether we get the temperature of 45 degrees centigrade and the heat flow rate of 6.28 kilojoule per second or kilowatt or not. So coming to the Aspen part, we will first add the component water, then we will add the property package, which is steam TA, then we will run the simulation. And once the results are available, we will go to the simulation blocks in exchanger, we will select heat X and we will do the connections hot in, hot out, cold in, cold out, control A, control B to align it. We can replace the nomenclature, but we can go like that as well. To specify the hot side, it is 80 degrees centigrade at inlet 1 atm pressure. Mass flow rate is 0.03 kg per second, while that of the mass fraction is 1. Since it's only water, so either you specify mass fraction or mole fraction, it will remain 1. Then specifying the cold side inlet, 30 degrees centigrade, 1 atm, mass flow rate is 0.06 kg per second, and then the mass fraction of water is 1. We have specified our both hot and cold streams. Then going to the heat exchanger, shortcut, there is no specification of it. Then hot stream outlet temperature, that is 30 degrees centigrade. Then we will click on this run button because we have specified or we have given all the specifications. So now we will go the thermal results and you can see the outlet temperature is 45.0261. The inlet temperature of the cold side is 20 degrees centigrade, while that of the outlet temperature is 45.0261. The inlet temperature of the hot side is 80, outlet temperature is 30. It is in calories per second, so converting it to kilowatt or kilojoule per second, it is 6.266, and there are too much decimals. Going to the heat exchanger details, the heat duty calculated, the surface area, the required area, all the information is given to us. So this is the second part of our today's video. Now coming to the third part, which is the comparison of manual calculations with Aspen calculations. You can see manually we calculated the outlet temperature as 45 degrees centigrade, while from Aspen it is coming out to be 45.03. If you see the percentage difference is less than 1%, which means that this is allowable. Similarly, the duty is 6.27, approximately 6.27 kilojoule per second or kilowatt from Aspen calculations, while from manual calculations it is 6.28, again in the range or in the acceptable range. So you can see that manual calculations and Aspen calculations are complementing or overlapping or nearly same. So that shows that our manual calculations are also okay and our Aspen results are also fine, and this model can be further used for optimization or further purposes. So this is how you use the manual calculations first and then verify it using Aspen. So I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer it. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.